4.6 Applied Optimization. The outline of this video is as follows. We will discuss a general strategy for solving applied optimization problems, which are problems that ask for the best possible value of a function. Then, I will walk you through several practical examples to see this strategy in action. First, we will look at two classic geometry problems: how to maximize the volume of an open-top box, and how to design a cylindrical can that uses the minimum amount of material for a given volume. After that, we will explore a fascinating application in physics, using calculus to derive Fermat's principle and Snell's law of refraction, which describes how light bends. Finally, we will turn to economics, where I will show you how to maximize profit by analyzing the relationship between marginal cost and marginal revenue. By the end, you will have a solid framework for tackling a wide range of optimization challenges. We can solve applied optimization problems using a reliable 5-step framework that turns a word problem into a solvable calculus problem. The first 3 steps are about setting up. You read the problem to understand the goal, draw a picture to visualize it, and introduce variables to translate the setup into mathematical language. The most important step is fourth, where you write an equation for the quantity to be optimized, such as area or cost. You will often use a constraint to rewrite this equation as a function of a single variable. For instance, if you are building a rectangular garden with a fixed length of fence, the perimeter constraint allows you to express the area using only one side length. Finally, with the function established, you use calculus to test the critical points and endpoints of its domain to find the absolute maximum or minimum. This structured process is the key to correctly translating a real-world scenario into a function to be optimized. Let us begin with a classic optimization problem, which is finding the maximum possible volume for a box made from a flat sheet of material. We'd start with a square sheet of tin, 12 inches on each side, and we will cut out a smaller, identical square from each of the 4 corners. I will define the side length of these cut-out squares as our variable, x. After cutting out the corners and folding up the sides, the height of the box will be x, and the base will be a square with sides of length 12 minus 2x. This gives us a volume function, v of x, which equals x times the quantity 12 minus 2x squared. The smallest possible cut is 0, and the largest is 6 inches, so the domain for x is the closed interval from 0 to 6. Our goal is to find the value of x in this domain that makes the volume as large as possible. Now that we have our volume function, let us use calculus to find the exact value of x that maximizes it. To do this, I will find the function's critical points, which are the places where its rate of change, or its derivative, is 0. First, I will calculate the derivative of the volume with respect to x, which simplifies to 12 times the quantity 2 minus x times the quantity 6 minus x. Setting this derivative to 0 reveals 2 potential critical points: x equals 2 and x equals 6. Since x equals 6 is an endpoint of our domain, the only interior critical point is at x equals 2. Finally, I will test the volume at this critical point and at the endpoints of the domain, which are 0 and 6. The volume is 0 at both endpoints, but at x equals 2, the volume is 128 cubic inches. This confirms that cutting 2-inch squares from the corners will produce the box with the greatest possible volume. Let us apply our optimization strategy to a classic problem: designing a 1-liter can that uses the least amount of material. First, we translate the physical properties into mathematical equations. The amount of material corresponds to the can's surface area, which is our objective function to minimize, is given by the formula A equals 2 times pi times r squared plus 2 times pi times r times h. The can must hold exactly 1 liter, or 1,000 cubic centimeters, which is our fixed constraint. The volume formula is pi times r squared times h equals 1,000. To analyze this with calculus, We need the area as a function of a single variable, so we solve the constraint for height, getting h equals 1000 over the quantity pi r squared. Substituting this back into the area formula gives us our final function to minimize. A of r equals 2 times pi times r squared plus 2000 divided by r. Now we have a clear goal. Find the radius r that results in the minimum possible surface area. To find the exact radius that minimizes the can's material, we will use our area function and calculus. First, I take the derivative of the area with respect to the radius, which gives us the expression dA dr equals 4 times pi times r minus 2000 divided by r squared. Next, I set this derivative to 0 to find the critical points, which are the only candidates for a minimum value. Solving this equation for r shows that the optimal radius is the cube root of the quantity 500 over pi, or about 5.42 centimeters. To confirm this is a minimum and not a maximum, we can check the second derivative, which is positive for any positive radius, meaning the function's graph is always concaved up. This gives a corresponding height of about 10.84 centimeters. The key insight is that the most efficient can has a height exactly equal to its diameter. This graph shows us why an optimal design for our can exists by plotting its total surface area as a function of its radius. On the vertical axis is the surface area, representing the amount of material we want to minimize, and on the horizontal axis is the radius. Notice the behavior at the extremes. When the radius is very small, the can must be extremely tall and thin, and you can see the surface area becomes very large. Conversely, as the radius gets very large, the can becomes short and wide, and its area also becomes large because of the huge top and bottom circles. The D shape of this curve shows that between these extremes, there is a single radius that gives the lowest possible surface area. This graph confirms our intuition that there is one ideal set of dimensions that will use the least material. Let us apply our optimization strategy to find the largest rectangle that can fit inside a semicircle of radius 2. First, I will place the semicircle on a coordinate plane centered at the origin, which gives us the equation y equals the square root of the quantity 4 minus x squared. If I set one corner of the rectangle at a point x, y on this curve, its height is y and its full length is 2 times x. This means the area we want to maximize is a function of x, a of x, which equals 2x times the square root of 4 minus x squared. To find the maximum, I will take the derivative of this area function and set it to 0, which reveals a critical point where x equals the square root of 2. After testing this value and the domain endpoints of 0 and 2, we find the area is 0 at the endpoints, but reaches its peak at our critical point. The largest possible rectangle has an area of 4. Let us apply our optimization skills to a famous physics problem involving how light travels, which is governed by what is known as Fermat's principle. This principle states that light always follows the path that takes the minimum amount of time, which is not always the shortest distance. Imagine a ray of light traveling from a point A in one medium, like air, to a point B in a denser medium, like water, where its speed changes. The path will consist of two straight-line segments connected at a point P on the boundary. Our task is to find the exact location of this point P that makes the total travel time as small as possible. We can express this total time as a function of the position of P, which we call x. The time in the first medium is its distance, the square root of a squared plus x squared, all divided by the speed x1. The time in the second medium is its distance, the square root of b squared plus the quantity d minus x squared, all divided by the speed c2. Our goal is to find the value of x on the closed interval from 0 to d that minimizes this total time function. Now I will show how finding the minimum travel time for a light ray, a core calculus problem, actually derives a fundamental law of physics. To find the path of least time, we must take the derivative of our time function with respect to x and set it to 0. This derivative, dEt dx, looks complex, but we can simplify it by recognizing that its components are related to the geometry of the light path. The first part of the expression is simply the sine of the θ1, our angle of incidence, divided by the speed of light xc1. The second part is the sine of the θ2, the angle of refraction, divided by the speed c2. When we set the full derivative to 0 to find the minimum, we find that the sine of θ1 over c1 must equal the sine of θ2 over c2. This powerful result is Snell's law of refraction, which explains why a straw in a glass of water appears bent. The path of least time is not a straight line, but is governed by this elegant relationship. We can use our optimization tools to find the production level that maximizes profit for a business. To do this, we model the company's finances with 3 key functions. Revenue is the income from selling a number of items, cost is the expense to produce them, and profit is simply revenue minus cost. The crucial insight comes from looking at their derivatives. The derivative of revenue is called marginal revenue, which you can think of as the extra income from selling one more item. Likewise, the derivative of cost is the marginal cost, or the expense of producing one more item. To maximize the profit function, we find where its derivative equals 0. Since the derivative of profit is just marginal revenue minus marginal cost, setting it to 0 means the two must be equal. For example, you should continue making a product as long as the extra revenue is greater than the extra cost. The ideal point is where they are the same, so remember that profit is maximized when marginal revenue equals marginal cost. This graph helps us visualize the relationship between revenue, cost, and profit to find the ideal production level. The profit at any point is the vertical distance between the revenue curve, R of x, and the cost curve, C of x. Initially, cost is higher than revenue, which means the company operates at a loss. After the curves cross at the break-even point, revenue becomes higher, and the company makes a profit. Our goal is to find where this profitable gap is widest. This point of maximum profit occurs where the slopes of the two curves are identical, which is the visual meaning of our condition that marginal revenue must equal marginal cost. Do not confuse this with the break-even point, where the total revenue and cost are equal, not their rates of change. To maximize profit, you find the production level where the cost of making one more item exactly matches the revenue from selling it. Let us apply our profit maximization rule to a concrete example for a company making MP3 players. The first step is to find the marginal revenue and marginal cost by taking the derivatives of our given functions. We find a constant marginal revenue of 9 and a marginal cost of 3x squared minus 12x plus 15. Setting these two expressions equal to each other gives us a quadratic equation, which we solve to find the two critical points where profit could be at a maximum or a minimum. The solutions are 2 minus the square root of 2 and 2 plus the square root of 2, which are approximately 0.586 and 3.414. To determine which point maximizes profit, we use the second derivative test. Since the second derivative is negative at the larger value, we can confirm this production level corresponds to a maximum. Therefore, the company should produce about 3.414 million players to achieve the highest possible profit. Let us bring together our strategy for applied optimization, which is all about finding the best possible outcome in a real-world situation. The core idea is to translate a practical problem into a mathematical function of a single variable. We typically start with a quantity to maximize or minimize, and then use a given constraint, like a fixed amount of material, to eliminate any other variables from our equation. Once we have that function, we use our calculus toolkit finding derivatives, locating critical points, and checking endpoints archi-sto pinpoint the optimal value. For example, the process for finding the dimensions of a can that minimize surface area is the same one used to find the production level that maximizes profit, where marginal revenue equals marginal cost. The essential takeaway is that this method provides a universal framework for turning complex optimization questions into straightforward calculus problems. Let us quickly review the two core strategies we have used to solve optimization problems. First, we often need a constraint equation because the quantity we want to optimize, like the volume of a can, initially depends on two variables, such as radius and height. The constraint, for instance a fixed amount of material, gives us a relationship between these variables. This allows us to rewrite our volume formula in terms of just a single variable, making it possible to find the maximum using derivatives. Second, in our economic model, we maximize profit by setting marginal revenue equal to marginal cost. This is because if marginal cost were greater than marginal revenue, it would mean that producing one more item costs more than the revenue it generates. For example, if it costs $3 to make the next widget, but it only sells for $2, you are losing profit on that unit. Therefore, the constraint equation sets up the problem, and the marginal cost rule finds the optimal solution.